In the last video, we talked about electron geometries. But in chemistry, we're often more interested in the molecular geometry. Molecular geometry is typically what we think of when we talk about the shape of a molecule. When it comes to molecules like the ones that make up DNA or enzyme proteins or the ones that are in some medications, shape matters. One thing that makes molecular geometry different from electron geometry is that molecular geometry does not include the lone pair electrons. It includes only the bonding regions. However, because electron geometry is what ultimately determines a molecule's shape, we need to think about these invisible lone pairs because they affect the molecular geometry. Lone pairs are negatively charged and they repel other electron domains, hence bending molecules into the shapes we know and love. One way to see the relationship between the molecular and the electron geometry is to begin by imagining the electron geometry. Now, make the lone pairs invisible. They're still there, repelling the other electron domains, but you don't see them. You only see the bonded atoms. The shape that's left after the lone pairs become invisible is the molecular geometry. Every molecule has both an electron geometry and a molecular geometry. Because electron pairs are invisible, the molecular geometry we see when we look at just the bonds may be only a part of the electron geometry. Let's look at water, for example. The electron geometry is tetrahedral, but the molecular geometry is not. It's bent. I want to digress here and talk about how adding lone pairs affects the bond angles. Each shape has a characteristic bond angle. For example, a tetrahedral molecule has a bond angle of 109.5 degrees. However, the lone pairs tend to repel a little more than bonded electrons do. The more lone pairs there are, the more they repel and squish down the angles between bonded regions. So for water, instead of having a bond angle of 109.5, the bond angle is closer to 104.5 because of the two lone pairs squishing those bonded regions towards each other and shrinking the angle. Tables like this show the different molecular geometries, each of which is associated with a particular electron geometry. We can better appreciate this using this PhET simulation. Let's look at the linear geometry. There's only one way this can happen without lone pairs, so the molecular and the electron geometry for the linear shape are always the same. When we get to the trigonal planar geometry, there are two possible shapes. If all of the electron domains are bonding domains, we get a trigonal planar shape with angles of about 120 degrees. But if we replace one of those bonds with a lone pair, it will squish the bond angle down to a little less than 120 degrees because electron pairs take up a little more space. To get the molecular geometry, we make the electrons invisible and voila, we have a bent molecular geometry. Tetrahedral geometries have 3 molecular variations. If there are no lone pairs, the molecular geometry is the same as the electron geometry. It's tetrahedral, and the bond angle is going to be 109.5 degrees. If we replace a bond with a lone pair, the bond angle will be squished to a little less than 109.5. If we make this lone pair invisible, we will get a trigonal pyramid. That's a 3-sided pyramid. If we swap out another bond for another lone pair, we'll get a bent molecule. The angle will be less than 109.5 because the two lone pairs take up a lot of space. This is the typical molecular geometry for water. Let's move on to the trigonal bipyramidal shape. If you have 5 bonded atoms, the shape will be trigonal bipyramidal. The angle on the top and the bottom will be 90 degrees, and the angles around the middle will be 120 degrees. If we swap a bond for an electron pair, we'll get a seesaw shape. If you replace another bond with a lone pair and make those lone pairs invisible, you'll get a T-shape. If you replace another bond with a lone pair, you'll get a linear shape. Let's move on to the octahedral electron configuration. If you have 6 bonded electrons, you have an octahedral shape with 90-degree angles. If we take one of those bonding domains and swap it in for a lone pair, we'll get a square pyramidal shape. The lone pair will squish the angles into something a little less than 90 degrees. If we swap out another bonded region for another electron pair, we'll get this square planar shape. We can keep going to get a T-shape and a linear shape as well. You should now understand the relationship between electron geometry and molecular geometry, and how electron geometry ultimately determines the molecular shape. You should also understand how molecular geometry is going to be different depending on how many lone pairs there are. You should also know that lone pairs tend to affect the bond angles in molecular structures, and they make them less than what would be predicted if the structure did not have lone pairs.